Today we will see how to prove the theorem limit x approaches to 0, tangent x over x is equal to 1. We need to prove on the left hand side we have limit as x approaches to 0, tangent x over x. We know that tangent x can be written as sine x over cosine x. When I do that, this question becomes limit x approaches to 0. On the numerator, I will have sine x, and in the denominator, I have a cosine x. That cosine x can be combined with the x already existing in the denominator. Therefore, I'm going to write down the denominator as x times cosine x. What can you say about this part of this limit? Limit x approaches to 0, sine x over x. During our last discussion, we proved that limit as x approaches to 0, sine x over x is equal to 1. Therefore, this part is equal to 1. Now, this question has become as limit x approaches to 0, 1 over cosine x. For that, we can do the direct substitution x equals 0. When we do that, we have a cosine 0 term in the denominator. We know that cosine 0 is equal to 1. Therefore, the answer of this limit is equal to 1. That completes the proof of the limit x approaches to 0, tangent x over x is equal to 1. We will also discuss a couple of examples. But before talking about the examples, let's revisit the theorem. Please note that this theorem also requires that the exact same figure is appeared in these three places, and that figure should approach 0. Then only our answer becomes equal to 1. Keep that in mind, and we will do a couple of examples. Here is your first example. Evaluate the limit as x approaches to 0, tangent 3x divided by 4x. Once again, what was the theorem we have? The theorem we have is limit x approaches to 0, tangent x over x equals 1. Pay attention to these three places. They all must have the same figure. But in this given problem, we have 3x right here and 4x in the denominator. So our first task is to convert that denominator into a term with 3x. Well, of course, we cannot change the question given. Instead, we can manipulate the numbers to get something directly similar to the requirements of the theorem right here. So what I'm going to do is, this is now equal to limit as x approaches to 0. We can write down this as tangent 3x divided by, instead of 4x, I'm going to write a 3x here and multiply that by a 3 on the numerator and write down the 4 in the denominator. Now, by doing so, I didn't change the question given, because if I pay attention on the simplification, you can see that the 3's will be cancelled. Therefore, this simply reduces to tangent 3x over 4 times x in the denominator. Therefore, I didn't change the question given. However, I do not need to simplify it as that. Instead, I'm going to keep this 3/4 outside and just look at the limit of this part right here. We have tangent 3x divided by 3x. All I need is this term to be 3x. Of course, if x approaches to 0, we can quite easily argue that 3 times x should also approach 0. Therefore, I can write a 3x right here. Now, I have completed the requirements for direct application of the theorem. Right here, and right here, I have the exact same figure, and that figure approaches to 0. Therefore, this part should be equal to 1. Therefore, our answer is equal to 1 times 3/4, which is equal to 3/4. Let's do another example. Here's your example number 2. Evaluate the limit as x approaches to 0, let's say this time from right hand side, sine 4x over tangent 5x. This is an example where we can use both of our theorems. So what are those two theorems again? We had limit as x approaches to 0, sine x over x is equal to 1. That was the first theorem we discussed. And today we saw the theorem that limit as x approaches to 0, tangent x over x is also equal to 1. For this problem, we can use both of them. However, in order to apply those theorems, I'm going to need x terms as well, with sine 4x and also with tangent 5x. Those x terms are not given in the question, but we can introduce them without change in the question. So how do we do that? To introduce the x terms, I'm going to divide both top and bottom by x. Let me write it this way. Limit x approaches to 0 from the right hand side. I have sine 4x on the numerator and I have tangent 5x on the denominator. What I'm going to do is I'm going to divide both top and bottom by x. Since I divided both the numerator and the denominator by the same quantity, I didn't change the question given. Let's proceed. Now for the numerator of this limit problem, we can apply the first theorem. Limit x approaches to 0, sine x over x being equal to 1. However, I need to modify this denominator to look like a 4x. And also to solve the denominator of this limit problem, we can apply the second theorem right here, which is the theorem that we proved today. However, in order to apply that theorem, I'm going to need a 5x right here. So let's go ahead and do those modifications. I'm going to rewrite this limit problem as it is. X approaches to 0 from right hand side. The numerator we have is sine 4x, that divided by x so far, and the denominator, let me write it this way. I will write limit x approaches to 0 from right hand side one more time. We have tangent 5x divided by x. Now what I need is I need a 4 right here. I cannot change the question given, therefore I will write a 4 right here and also I will multiply that out like this. Similarly, I need a 5 right here. Since I cannot change the question given, I will write a 5 here and write another 5 there as well. The reason for doing it that way is if I simplify, I can see that these 4's will be cancelled. These 5's will be cancelled. Therefore, I didn't change the question given. But we will not do that simplification. Instead, we will evaluate these two limits using the two theorems that we have. In order to evaluate the limit on the numerator, I need 4x to go to 0 rather than just x going to 0. However, we can simply argue if x approaches to 0, 4x should also approach to 0. Therefore, without any problem, I can simply write a 4x approaching to 0. Similarly, in the denominator, I will need a 5 right here. We can do that because if x approaches to 0, 5x should also approach to 0. Therefore, I can simply write a 5x right here. Now, we have a situation where our theorems can be quite easily applied for this part and for this part right here. As you can see, these three places have exact same figure and that 4x is approaching to 0, which means the numerator term right here should be equal to 1. Similarly, in the denominator, we have a 5x right here, 5x and 5x. All three places have the exact same figure and that approaches to 0. Therefore, according to our theorem, this part should also equal to 1. Therefore, our final answer for this problem should be 1 times 4 on the numerator divided by 1 times 5 on the denominator. Let's look at another third example. Evaluate the limit as x approaches to 1 from right hand side, cotangent pi x over 2 divided by 1 minus x. That problem doesn't look like something where our theorem can be directly applied. However, we can still apply that theorem for this question as well. All we need is we need to transform this cotangent function into a tangent function. That's our first step. We can use cofunctions. If you still remember basic trig, we know that cotangent pi over 2 minus theta is equal to tangent theta. This is a relationship from cofunctions. I'm going to use that with theta being equal to pi x over 2 and rewrite the numerator using a tangent first order term. Then this problem reduces to equals limit as x approaches to 1 from right hand side. On the numerator I will have a tangent function. It will be pi over 2 minus pi x over 2 divided by 1 minus x. Now we can do some further simplifications. You can see within that tangent function we have pi over 2 as a common factor. I'm going to factor that out. Please note that you cannot write it here because it is inside that tangent function. Therefore, we have to handle it inside the tangent function. So in the next line, I'm going to write this as limit x approaches to 1 from right hand side. We have tangent. I will open big brackets and then I will factor out pi over 2. Then I will open parenthesis. Once pi over 2 is factored out, inside parenthesis I must have 1 minus x, close parenthesis, close brackets. In the denominator I have 1 minus x. Now you can see that the things are slowly getting in order so that our theorem can be applied. In order to apply the theorem, I need whatever the figure right here to be exactly same in the denominator. And also it has to be the exact same figure with limits, and it should approach 0 as well, which we can see as a second step. For now, I need to change this denominator to look like pi over 2 times 1 minus x. How would you do that? I can simply write parentheses like this and write pi over 2 in the denominator and another pi over 2 on the numerator, so that I didn't change the question given. In case if I need to simplify, we can simplify those two terms and it is exactly the original problem. Now if I look at this denominator completely as one whole thing, we can see that we have tangent of a figure divided by that exact same figure. Now all we need is the limit of that figure to approach 0. Now we will see if that's the case. In fact, if your x approaches to 1, what can you say about 1 minus x? If your x is approximately equal to 1, 1 minus x should be approximately equal to 0. No matter from what you multiply 0, the answer will be approximately equal to 0. Therefore, we can argue that the limit can also be written this way. Limit pi over 2 times 1 minus x approaches to 0. But I have one more question. Does it just approach to 0, or does it approach to 0 from the left hand side or from the right hand side? Please note that your x approaches to 1 from the right hand side. Therefore, x is a little bit more than 1. If you look at this part, 1 minus x, since x is a little bit more than 1, 1 minus x should be slightly negative. That times pi by 2 should also be still negative. Therefore, pi over 2 times 1 minus x actually approaches 0 from the left hand side. Those tiny details may not be super important if you are in an entry-level calculus class. Anyways, let me go ahead and solve this problem. On the numerator, I have tangent pi over 2 times 1 minus x divided by pi over 2 times 1 minus x. In addition to that, I have this pi over 2 term on the numerator. So let me write it down as well. Times pi over 2. Now we have a situation where our theorem can be directly applied. What was the theorem again? We have limit as x approaches to 0, tangent x over x equals 1. I need these three places to have the same figure, and that figure should go to 0. In other words, you can remember this theorem this way. Limit a figure, such as a man, approaches to 0, tangent of the man divided by the man should be equal to 1. No matter what, whatever the figure you have in these three places must be identical, and that figure should go to 0. Then the limit is going to be equal to 1 when you have the tangent function, just like with the sine function. Therefore, all of this part is equal to 1. That times pi over 2. Therefore, our final answer should be equal to pi over 2. Alright, I will stop the video at this point. If you have any questions, please feel free to let me know. Thanks.